identifying whether a trinomial is a perfect square trinomial or not. Here, we will just be using PST as the acronym of perfect square trinomial. In doing so, we need to answer the following questions. Are two of the terms perfect square? Second, is the remaining term equal to twice the product of the square roots of the two terms? If both answers to the questions are yes, then it is a perfect square trinomial. Otherwise, it is not. Let's have some examples. Number 1, here, the first and third term are perfect squares. Getting twice of the product of their square roots, we have. Notice that we use positive 9 instead of negative 9 because the remaining term has a positive sign. Otherwise, we will use negative 9. Now, since 18x is equal to the remaining term, we can say that a trinomial is a perfect square trinomial. For number 2, here, the first and last term are also perfect squares. Getting twice of the product of their square roots, we have. Note that we use negative 5y as the square root of 25y squared instead of positive 5y, since the remaining term has a sign of negative. We'll use 5y if otherwise. Now, since negative 20xy is not equal to the remaining term, which is negative 10xy, we can say that the trinomial is not a perfect square trinomial. After knowing how to identify when is a trinomial a perfect square trinomial or not, we can now proceed to identifying the factors of a perfect square trinomial. In factoring perfect square trinomial, we will be going to identify the binomial that when multiplied by itself, it will give us the trinomial given. That can be done by, first, identifying the square root of the two terms that are perfect squares. Second, by using sign of the remaining term of the trinomial between these roots. Finally, raising the obtained binomial to the second power. Let's have some examples. For number 1, after knowing that a trinomial is a perfect square trinomial, we identify the two terms that are perfect squares and identify their square roots. We then use the sign of the remaining term between the roots. Finally, raise the obtained binomial to the second power, and we have. For number 2, we can notice that we can reduce the given polynomial by factoring it out using common monomial factor, which is 2x. And we have the factors. We can observe that the second factor is actually a perfect square trinomial, and therefore, we need to factor it out. Get square roots of the two terms that are perfect squares, which are. So we have. Use the sign of the remaining term between the roots. Raise the obtained binomial to the second power, and we have. Since this is just the factored form of the PST, we still need to write 2x as part of the factors, and this will be our final answer. For number 3, we can notice that 3 of the terms can be grouped having a PST, and these terms are. So we have. Getting the square of a binomial form of the trinomial, we have. Copying the 16 as the first term, we have this. And still, this can be factored out using difference of two squares. We have. For number 4, let's try to group the terms. In this example, notice that if the x and the y's are grouped, we'll be lacking another term for PST. So we try to rename the remaining term, which is negative 7, into 9 minus 16. We have. From the renamed term, we can now have two PSTs. We have. Rewriting these PSTs to square of a binomial form, we get. With this, we can still factor it out using difference of two squares, giving us the final answer For number 5, in this given, we first try to simplify each term by using distributive property. Then we have. Now, regroup the terms having two PSTs. We have. Rewriting these PSTs to square of a binomial form, we get. With this, we can still factor it out using difference of two squares, giving us the final answer